So last time we concluded that in dielectrics, the integral of D by S over the surface S would be the same as the total free charge enclosed, and this was our Gauss's law in dielectrics. And we had moved to the special case, where the special case was for linear dielectrics. So in linear and isotropic dielectric, the polarization P is proportional to the electric field. To the electric field intensity E, so we can save on our pens. And of course, that is true because whatever bound charge we are getting on the sides of the dielectric are bound to be there because of the free charges which are existing on the plates. And it is these free charges which are bringing about F minus plus minus F free, which are bringing about this bound charge on the surface of the dielectric and this other one on the surface of the dielectric. If you remove the free charges on the other plates, you won't have any bound charge. So our P is equal to epsilon naught chi E, then E. Of course, where chi E, if you recall from electricity and magnetism, was called the susceptibility of a given material, for example now a dielectric. So if we follow Minister's words, putting on the scar is the chi E, or maybe we can call it the chi I. So when he was saying that when you put on a scar, you become susceptible to red. So that's susceptibility. If a material is able to allow electric fields to go through it, is what we call the susceptibility, the electric susceptibility of that material. And the constant, this constant chi E is called the electric susceptibility of the medium, or what we now call, or what we call as the dielectric. So in linear and isotropic, in this linear and isotropic media, which we call dielectric, where isotropic implies the properties of the media, the properties of the media are the same in all directions. We are meaning, when we talk of isotropic, we mean that all the properties of a given direction are similar on all sides. This may not be a good example, but what we are saying is that whether you look at it from this side or the other side, or from whichever angle, the properties of such a material is similar. Like if I chopped off such a marvelous piece nicely, really you may find that almost all its properties on either side, if it was, manufactured with precision. So then we have that we say that the electric displacement vector is equal to epsilon naught E plus the polarization. And then we say that if we substitute for K, would imply that we have D is equal to epsilon naught A plus epsilon naught chi A. And we can say that this would imply that D is equal to epsilon naught 1 plus chi E. Then we also take E outside. So not only is polarization proportional to the electric field applied, so is the electric displacement vector D. So if you look closely, you see that even D, because epsilon naught and 1 plus chi E are all constants, D also is proportional to the applied electric field. Just like we also said that P is proportional to E. So we can say that D is the same as epsilon E, where of course our epsilon, in some books, this epsilon is written as sometimes like that. So you need to know whenever you open a book, each author decides to use something that will make him or her special. So then where epsilon is the permittivity, of the medium. For this case, the dielectric. Permittivity means how is such a material permitting the electric fields to go through it. Whereas when it is allowing magnetic fields to go through it, we talk of permeability. How permeable is a material to magnetic field lines, we shall be talking of mu. Whereas how permeating a material would be, we will be talking of epsilon, which is the permittivity. If it is a free space, then we talk of epsilon naught, which is the permittivity of free space. Thus, we can say that our epsilon is equal to this whole constant, which is equal to epsilon naught 1 plus chi E. And if we recall, please, can you always do me a favor? I paid so much money for that machine to use it as a clock. I didn't get any reimbursement from the university. So from epsilon is equal to epsilon naught, this would imply that epsilon naught is equal to epsilon over. And during your high school, you were only told that the relative permittivity is the same as the permittivity with the material or the dielectric divided by, or it was the ratio of the capacitor with the dielectric to the capacitor without the dielectric. So, where epsilon r is the dielectric constant. Dielectric constant, and it is known to be dimensionless. Why? Because the units of permittivity with the dielectric are the same as the units of the permittivity without a dielectric. They cancel out each other, and then we get the dielectric constant being dimensionless. Compare with epsilon equals epsilon r on 1 plus chi e. Then we shall get that our dielectric constant is equal to 1 plus chi e, which is equal to, because if I divide both sides by epsilon r will be equal to epsilon r that, which is equal to epsilon of epsilon r. The volume bound charge density in a homogeneous linear, that is a uniform linear isotropic medium, then we would have that rho bound is equal to minus divergence of the polarization. That is how the polarization diverges through into the material of the electric. And this would be the same as minus divergence of the epsilon naught chi e d divided by epsilon. Of course, since E is equal to d over epsilon, because we say that d is proportional to electric field intensity, since E is equal to d of epsilon, because we know d is equal to epsilon A, if we make this the subject, then we will get that using the free volume charge density on the plates. We know that the divergence of D is equal to rho free, and this was Gauss's law in differential form for dielectrics. And epsilon, we've already said, is equal to epsilon naught in 1 plus the electric susceptibility of the dielectric. Then this would imply that our rho bound would be equal to minus chi e over 1 plus chi e in rho free. But we know that 1 plus chi e is the dielectric constant. Thus, if we have to relate how much bound volume charge density we get due to the free volume charge density, then we would say that our rho bound is equal to minus chi e over epsilon r multiplied by rho free. Of course, as you can see in this expression, these two are constants. If you don't have any free volume charge density, you will never get a bound charge density. Such that we say that where we shall always have bound volume charge density equal to 0, you don't have any free volume charge or free charges available in your configuration. Any questions? So now we know how the bound charges are created due to free charges, and how we can relate the free charges and the bound charges. If we don't have any free charges, that is, if we don't have any charge on the plates, if we don't connect our plates to anything, let's say, if we don't have so with our switch open, if our switch here is open S, and we don't have any free charge, you wouldn't expect any polarization in the dielectric. It's until when you close the switch that you get the relationship being how permitting the dielectric is and how the dielectric constant of the dielectric itself that will be able to produce with an amount of bound charges to get that bound volume charges. If there are no questions, now we can try to understand how the electric displacement vector D and electric field density E relate across the boundaries. So we are looking at B and A and how they relate when they cross the boundaries, such that we first look at what we call the boundary conditions. So 2.0, we look at boundary conditions on the vectors D and E. How many of you have seen the reference books I uploaded? Are they nice? 2.1, you have boundary conditions. Boundary conditions. Let's start with the D on the normal component of D. I will invoke you to go back to your mathematics, and I won't have to spend a lot of stuff explaining how the divergence comes about and what is the definition of the divergence in terms of the limit and the small change or even part. But before then I use my demo. Unfortunately, I erased my thing and a few things got messed up. So I'll just first make them straight again. And some of you see me very brown, you think I'm too soft to break it. We shall, when we're looking at E, I'll use this stochastic loop. and you'll be able to understand the concept of the stochastic loop. But now I'm just going to show you the example of the pillbox that I have to take this part here as two. Let me use this side like this. So I'm taking two dielectrics, one dielectric or medium one being this one, and blue being medium 2. And after taking that, I'm just chopping out a piece to cover one inside the tap here and another piece in this other part to make a pillbox. That a pillbox that covers the conditions in the medium 1 and the medium 2. So if it were you, after opening your TV or computer, you were going to throw away this without any knowledge that it can act as a teaching aid. So consider the interface is this. The interface is this surface here in between these two dielectrics. So consider an interface. Consider an interface between two dielectrics. Between two dielectrics, or we can say between two dielectric media, where media is plural for medium, with a surface charge density, with a surface charge density rho free on the interface. So, because we want to have an ambivalent surface, I've showed you a stiff interface of two dielectrics, but as you can see in some of the dielectrics, like when you look at a cylindrical capacitor, which you will find in most radios, and in the lab you have seen it in the lab, where you have something of the sort, and you have two legs here. It's not that what is inside is because they got two dielectrics and then roll them up finally to make one side be in one of the plates and the other be in the other plate with a dielectric in between. So that's why I'm taking a case of, or that's why I will take a boundary, an interface of this nature. Although I showed you an interface which is stiff, but I'm not gonna, I don't know whether I drew it nicely. I need to try to invoke my, fine art. I was a good artist, but I feared two things after the embarrassing comment by one of the guys who found me trying to design something. I never told you this story. I was very young and working with the art teacher, and when I was drawing or writing the words, I remember it was called, they were supposed to be circular with a PO box in the middle. Then the guy came and looked at me and said, "Toto, how much are you making that for?" Told him 50,000. Do you think because he was not the owner, he was inquiring also to have it on his shop. So he said, "Do you think money is picked from a tree?" It hurt to me, You see, when people see you just doing your skill, like because it is a talent, they think it is easy. You come, you do like this, like I already have this circle, I put like this, and then say these are ears, then I put nice eyes, then put your dumb nose, and then put the lips, finish, and then try to put the hair. Someone said, but you took a short time. It's not my fault to have the talent. So, but I said I will never do fine art if I don't have any other qualification. If I want to do it, you first make terms. I just come because I got a skill and I can do good work, but not because you think I'm dependent on you. So I left it. But I got an A. That's not a secret. I have my certificate. 2 throughout. I had 2 in all papers on fine art. Final and A. We are very few. And I did not attend art lecture lessons at A level. I had done everything in O level vacation. So whenever the guy would ask, draw a composition of drought, I'll just go in my archive, pick one, bring and I'm saying these things on camera. I'm very serious on that. Half pieces, I'll come with a piece of Virgin Mary with Jesus. One piece I made in my vacation of O level, and I'll make sure I show you on Thursday. I'll come with it so that you see the skill I have. Soon I will be trying to do it again. Soon, after I have taught and I've gotten tired, my hobby will be drawing art pieces, and I'll make a gallery. So if we take a piece on top, threaded in on the bottom, so I'll get a peel box. I drew this to show you where the interface is, okay? These dotted lines are to show you that this is along the piece of paper or along this here. So, but if I use our paper to represent our surface, I'm just taking a line along, dotted lines along the surface to show you that I'm going to make my peel box a little bit on the other side of the interface into medium 2, and a little bit on the other interface into medium 1. So this would be the other side of the interface, and I'll draw this part to be one surface, side of the other surface, and then on top as our surface. And then I will say this is, below here is medium 1, and up here is medium. So I don't think now you get confused, because I'm talking about medium 1 being down here, and medium 2 being up here, taking this thing to be the interface. And we are having this surface or interface having free charge density sigma free, and this is our peel box. And of course, we only can understand or apply our Gauss's law on this peel box by getting to know how much is going through normal to the surface of our peel box. So I will have my normal to this peel box running from medium 1 to medium 2, and this is to show that it is a normal unit direction vector from running from medium 1 to medium 2. And I will prolong that in on the other side. If you can draw some, dotted lines to show you that it is inside the interface. And then I'm having D1 entering here, and I'm having D2 coming out. If you can recall, we did this kind of stuff in electricity and magnetism. dielectrics part. So we weren't doing it for fun, and that's why I told some of you that this course is going to be simple. So this surface here is ds, and let's take this height of the pillbox to be h, small h. So far we have our diagram done. All we now need to do is to understand what is going on. So by definition of the divergence of the electric displacement vector, so when you diverge D through an interface is what we are trying to understand. When you try to make it diverge through an interface, that means you are taking divergence of D. This will be defined as the limit as the change in the volume tends to 0 into 1 over the change in volume double integral D dot n12 ds. Of course, in some books, you'll find that this one can be represented as ds. But just because we want to show where the normal component, the normal unit direction vector is coming from to, then we just leave it as n cap, n12 cap ds. And this can be taken as the limit as the pillbox becomes tinier, which is tending to 0, and we express our volume as the product of the surface and the height h, d2 minus d1 dot n12 roof ds. Of course, where the tau is the volume, or the element of volume is the volume of the pillbox, which is the base cross-sectional area multiplied by the height h. This pillbox of height h and cross-sectional area yes, encompassing or cutting across, encompassing the two media, such that tau is equal to ds multiplied by h. So I guess I gather that now you have drawn this and it is stuck in your mind, so that I can wrap it off and we move on with our algebraic gymnastics. Don't worry if I grab it off. Once you're on the way, you got all you want. But of course, we know that the divergence of D is not to be rho f, the free volume charge density. We did that as Gauss's law in differential form. So that means our expression will now become that the limit as h tends to 0 of H divergence of D is equal to the limit as H tends to 0 of rho F H, and this should be equal to the free surface charge density, and hence I can comfortably say that N12 dot D2 minus D1 is equal to rho free, but for homogeneous and isotropic media, we have that D2 is proportional to epsilon 2, which is epsilon R2, E2, and D1 is equal to epsilon R1, E1, where epsilon R2 and epsilon R1 are the dielectric constants of medium 2, or we say media 2 and 1 respectively. Therefore, if you have any thought or comment, yes, please let me know. So, if we now know that, therefore, we shall have that N12 that D2 minus D1 will be equal to, by substitution, N12 cap that whole range of epsilon naught, epsilon R2, E2 minus epsilon naught, epsilon R1, E1, and this should be equal to sigma free, implying that N12 that epsilon R2 grad V2 by substituting epsilon naught, by substituting E is equal to minus grad V, then we will have that minus epsilon R1, then grad V1 is equal to the minus, which should have been persistent on these two. We put it on this other side, and also the epsilon naught common to this, we put it as a denominator on the other side, such that we say that our epsilon R2 Kali V2 by Kali N minus epsilon R1 Kali V1 by Kali N is equal to minus sigma free of epsilon naught. And this gives us, where of course our Kali by Kali N denotes denotes differential along the number, the outward number to the interface. So we are looking at it as being this normal to the interface, being our Kariba Kariya. And that is by saying that graph of area is Kariba Kariya and along the normal. So, tomorrow we shall be able to see or to look at the relationship or the boundary condition for the tangential component of E. So we can say tangential, this was a normal component, and as you can see, if we do not have any free charge in the middle of the interface, then we would have that B1, B2 minus B1, that will be N1, 2 will be equal to 0. If rho F is equal to, and we will say that it is continuous. So 2.2 is the boundary condition. Boundary condition on the tangential component of of E. Pardon? This one. From this. Okay, so I guess you are translating, and I have these people outside very anxious with their knowledge. I'm giving this